Yes, so our last speaker of today is Quim Juan from University Massachusetts Amherst, and he's going to talk about exploring or exploding primordial black holes. Maybe I'll send you a reminder when 5 minutes are left.
Okay, yeah, thank you. Okay, well, thanks, Anish, for inviting me. It's really my pleasure. Yeah, my name is Kim. I'm a postdoc at the University of Massachusetts, and today I want to talk about exploding black holes, actually primordial black holes, to be concrete. And yeah, I just noticed when you sent the email, probably that was my typo, but the title of the talk was Exploring with an R, Primordial Black Holes. Probably I wanted to write Exploding black holes, but it's fine. The typo makes complete sense because in the end I'll talk about exploring exploding black holes. So fine, just take the title you prefer. Okay, so this talk is based on three papers, well, actually two papers that are available on the archive, and one paper that should be available very soon, hopefully next month or so. And all of these three papers are in collaboration with the group UMass, so Michael Baker and Andrea Tam, who are professors, and Aidan Simons, who is a grad student. Okay. So yeah, let me start with a very brief introduction on PBHs. You might know that they were firstly discussed in the 60s and 70s by these people, Seldovich, Novikov, and Karen Hawking. And typically, primordial black holes are formed in the early universe from the collapse of large overdensities when upon horizon reentry. And I think it's always interesting to look at the historical evolution of the interest of the community on PBHs, as you can see in the plot here. Well, you said initially the interest of the community was quite low. Actually, well, you see only just 1 to 2 papers being published, mostly from these people, Carl Hawking, Novikov, etc. There was a small spike of interest in the 90s due to a microlensing survey reporting positive results, saying that part of the dark matter, a significant fraction, could be in the form of dark compact objects, so for instance, primordial black holes. Although a microlensing survey that appeared later updated the results and said that that wasn't the case. Only a very small, tiny fraction could be in the form of dark compact objects. And so in the end, the interest in PBHs only took off in 2015 after the first observation of gravitational waves by LIGO. So you can see here it's marked with a star. And then after that, there's basically an exponential increase in the number of papers that include the words primordial black holes. Those are papers on Spire-Hep, by the way. And I think well that's interesting because that shows a very stark contrast with the situation 50 years ago and now. And you might wonder why people are so interested. Do we actually have any observational evidence of primordial black holes? Do they know if they even exist? Well, before answering this question, let me try to convince you that we might have an evidence, although the answer, spoiler, is going to be no. The reason why some people maybe might think primordial black holes exist and we will eventually detect them can be, well, in this list that you've seen the slides, we have observations with LIGO of black holes that fall in the pair instability gap that are sort of difficult to explain from standard astrophysical phenomena. So maybe these black holes might be PBH, maybe not. We have also observed very massive black holes at very high redshift that challenge our understanding of how accretion onto black holes work. So maybe those black holes came from an initial PBH, maybe not. More recently, we also have this detection by the nanograph collaboration, which reported the observation of a stochastic gravitational wave background, which might.
Sorry, the second point is which experiment is this? Is this the JWST?
Yeah, exactly. Yeah, yeah.
Okay.
Um, So this background might come from well, could be associated to the formation process of PVHs. And there are other observations. For instance, I'll talk about the KM3 net event later in this presentation. Uh, um, and so, well, for those who follow the literature on PBHs, you might know that a lot of people feel very enthusiastic about PBHs. For those who don't follow the literature, here there's a list of recent papers that really present PBHs as well, the new holy grail or something. And maybe you get the feeling that people are very optimistic, right? But the truth in the end is that so far we do not have any observational evidence, and that's well, important to keep in mind. There are many phenomena that could be explained with PBHs, but in the end, data tells us how well the universe looks like, and there's no observational evidence for primordial black holes. Okay, so well, in this talk here, I try to convince you that we might observe primordial black holes in the coming years. There are several ways we could observe primordial black holes. The observation could come from different channels. Of course, it could come from the gravitational wave channel. I discussed some of the observations already. However, this presentation will be about detecting primordial black holes via gamma rays and also neutrinos, actually. And so I'll try to convince you that this is something that can possibly occur in the next years. And it's also probable. It's both possible and probable. But before we get to this point, let me discuss some details about the basics of PBH evaporation. Okay. So you might know that black holes possess a temperature that's inversely proportional to the mass of the black hole. And on the left of the slide, I'm showing you the expressions for the temperature of a Schwarzschild black hole. So a black hole that's just characterized by its mass. And a Reissner-Nordstrom black hole. So it's a black hole that's characterized by the mass and the charge Q. You can see in both cases the temperature is inversely proportional to the mass. And we can compute the emission of a black hole that has a temperature T. This is the so-called Hawking radiation that follows an almost black body distribution, as you can see on the right. It's not a black body distribution. It's corrected by the gray body factor, this gamma function here, that depends on the properties of the black hole, so the mass, the charge, the spin, if it's a spinning black hole, but also the properties of the emitted particle, so the spin of the particle, the energy. And so it deviates, it makes this distribution deviate from the exact black body distribution. So it's called gray body distribution. And so it's important to know that black holes will radiate all fundamental particles whose mass is below the black hole temperature, roughly. So that means that it doesn't matter which is the coupling between particles. Black holes will emit all particles, not only standard model particles, but also any other particle that might be beyond the standard model. And that's a very interesting observation because, as I will discuss later in this presentation as well, this gives us the opportunity to probe dark sectors if we are able to observe an evaporating or an exploding black hole. And I will discuss that in more detail in the coming slides. Okay. So as I said, black holes radiate all fundamental particles, standard model plus any possible BSM particle. And that alters or modifies the evaporation history of the black hole. That's something it's represented in this plot here. So you can see here I'm plotting alpha, which is basically the coefficient that tells you, this is the page function it's called. This is the coefficient that tells you how this black hole evaporates, how fast it evaporates, as a function of the black hole mass in grams. And so you see for a very heavy black hole, that's a very cold black hole. So it will only emit those particles that are the less massive particles, photons, neutrinos, positrons, and electrons. And as the black hole evaporates, well, it gets hotter. So it starts evaporating into other particles. So, well, you can see here the QC phase transition, and then it includes heavier degrees of freedom, like the B and the charm quark, the tau, and then later the Z and the W boson, and the Higgs and the tau quark as well. And for black holes below 10 to 11 grams or so, the temperature is already so high that all standard model particles are being emitted. But if we have heavy particles beyond the standard model, or even a whole complete dark sector with, I know, so a given number of degrees of freedom, for instance, here 1 in green and 10 in red, uh, that activate at a given mass scale, so 10 to the 3 GeVs or 10 to the 5 GeVs, you see that this alpha function is modified. So then when the black hole gets hot enough, it will start emitting these dark sector particles as well. And so this can modify, for instance, the number of photons that a black hole will emit. And we can use this to distinguish between black hole emitting into just standard model and a black hole emitting into standard model plus some dark sector. Um, and again, this is something I will discuss in more detail if I have time later in this presentation. And yeah, something else I wanted to say about PVH evaporation is that we distinguish between two kind of particles being emitted. There's the primary particles, which are the ones that are directly emitted via Hawking radiation. And then there's the secondary particles, which are those particles that come from the primary particles and that arise due to processes like hadronization, decay, final state radiation, etc. So, for instance, you might think of well, just a particle that decays very fast, like a tau or whatever, like a tauon or something that it's evaporated by the black hole and then it decays into other particles. So these other particles are the secondary particles. And you can see the primary and the secondary spectra for different black hole masses in the plot on the right. And yeah, I just want to say as well that all these particle spectra here we can compute. We have numerical tools like HASMA, PCM, HCM spectra that we can use to compute this primary plus secondary emission. Okay. And so now, if we assume we have a population of black holes in the universe that are formed in the right after inflation, now, well, we know that they evaporate into photons, neutrinos, but also all sorts of particles. And if this abundance of black holes is large enough, well, they inject a significant amount of energy into the primordial plasma, and this can have some cosmological implications. And so people have studied these implications and have derived constraints on the allowed abundance of primordial black holes. And that's a usual plot that probably you've seen already when people talk about PVHs, that here I'm showing in the bottom right corner. This is FPVH, which is a fraction of dark matter in the form of primordial black holes as a function of the mass of the PVH at formation. And here I'm showing some constraints, the one from coming from BBN in red, TMB in blue, and the extragalactic gamma ray background in black. All the shaded regions are regions that are excluded. And this plot, by the way, that's for a monochromatic mass function. So assuming a population of black holes where all of them have exactly the same mass, which is not physical, but well, we can do the version of this plot for extended mass functions as well. And we could also go to black holes above 10 to 15 grams, and there are other constraints. But I'm not showing them because in this talk, as I said, I will focus on black holes that evaporate and explode. So this range of masses here is the one that will be relevant for the coming slides. Okay. Okay. So as I said, the temperature of the black hole is inversely proportional to the mass. So as the black hole evaporates, it loses mass, so it gets hotter. So it leads to a larger emission. It emits more particles, which are more energetic, which in turn makes the black hole become lighter even faster, so hotter even faster, and so on and so forth, in a sort of runaway process that is known as explosion. And well, these explosions, they emit very high energy particles, and in particular gamma rays and neutrinos, which are particles that we know very well how to detect, and we have telescopes that can detect those particles. So yeah, I'll focus on the emission of this sort of particles. Um, Okay, yeah, that's a more visual depiction of the exploding of an explosion of a black hole. So in the plot here, I'm showing the temperature of a schwarzschild black hole as a function of the remaining lifetime of the black hole. So you see that the orange line increases kind of steadily at first, but then the jump in temperature is very quick and very sudden. So it is these final stages of the PVH evolution that we call explosion, right? When the temperature increases by several orders of magnitude. So it really looks like an explosive event. And well, of course, I hope you agree with me that the detection of black hole explosion would be well, awesome for many reasons. Well, first of all, it would provide evidence for primordial black holes, right? Because any black hole that explodes today has to be primordial. Black holes that form from stars are too massive to explode anytime soon. So if we're sure we're observing an exploding black hole, this has to be primordial. The second reason is that, well, observing an exploding black hole would provide evidence for Hawking radiation, which so far it's still a theoretical prediction. So that would give experimental proof for that. And the third one, which I already briefly discussed in the previous slide, is that we can use, if we're able to detect this explosion and we have some quality observation, we can extract information about the extra degrees of freedom beyond the standard model. So we can say something about what particles exist in nature beyond the ones that we already know. And Right. And so I'd like to compare the the possible observation of an exploding black hole with the supernova 1987A. This event was observed in 1987, and it was a very cool and amazing observation, and it allowed us to study the properties of supernovas, but also the properties of many physical phenomena. For instance, the core collapse supernovae. It gave us a lot of information about neutrino physics, axion physics as well, about the stellar evolution, etc., etc. And even now, there are papers that still use some constraints or some information that's derived from this observation. So I like to compare this observation with a possible observation of an exploding black hole, in the sense that it would provide many insights into many fundamental physics questions. And so basically, my point here is that we have to be ready for the observation of a PVH explosion. Because if we manage to get a very high quality observation, then we can say a lot of things about many things in physics. Fine. And so a good news is that we know and we can observe a primordial black hole exploding. We have telescopes that are currently working, for instance, HOG and LASSO, which actually they have already looked for exploding black holes, and so far they have detected none. So they placed upper limits on the local burst rate. So for HOG, it's around 3,400 explosions per cubic parsec per year, while LASSO sets a more constraining bound of 181 explosions per cubic parsec per year. And not only we have telescopes that are currently working, we also have future telescopes that will be working very soon, like CTA, which also release a prospective limit of 36. So you see, we're doing a good job in bounding the local burst rate for primordial black holes. So that's pretty cool. We know how to observe a black hole. We can actually do it. We are already looking for them, and we could extract a lot of information from an exploding black hole. But of course, there's some issues here, and it has to do with the following. So black holes that we are going to observe today, black holes that explode today, correspond to a given formation mass. So in the standard scenario where we assume Schwarzschild black holes evaporating into just standard model species, only those black holes that are formed with a mass around 5 times 10 to 14 grams in the early universe are the ones that have a lifetime of the age of the universe, roughly. And if we have a significant population of these black holes, well, they emit all sorts of high energy particles, and in particular gamma rays. And so we would also expect to observe some observational signature in the extragalactic gamma ray background. And we don't, so we can constrain the abundance of these black holes to very low, uh, uh, to very low abundances. And well, here in the plot, you can see that FPVH is around 10 to the minus 10 or so. So, well, what happens here is that, sure, we might have black holes, Schwarzschild black holes that explode today, but the abundance we expect is very low. And so that leads to extremely low burst rates. And in other words, if we consider that the telescope, like Hawk and Lasso, can resolve a PBH explosion as far as around 0.1 parsec or so, and motivated burst rates taking into account these bounds on FPVH are around 0.1 explosions per cubic parsec per year. That means that if we want to observe just one exploding black hole, we'd have to wait for 10 to the 4 years, something like that. So it's extremely unlikely for us to observe an exploding black hole in this scenario of Schwarzschild plus standard model black holes. And so that's kind of disappointing. And so with our group at UMass, we were wondering if we could enhance the local burst rate, if we could go beyond the standard picture for primordial black holes, so that this observation time is reduced, and it makes it more likely for us to observe an exploding black hole in the coming years. And so that's what I'm going to discuss now. Okay, so we make the question, how can we enhance the local burst rate? Well, so you have to know that the key object here is not just the abundance of black holes, so FPVH, but the number density, which depends both on the FPVH and then the mass of the black hole as well. And so we might have two scenarios here, the one on the left and the one on the right. The one on the left corresponds to a situation where we have black holes of the same mass, and we just increased the value of FPVH. So that if we increase FPVH, you can see from the formula above that this will increase the number density, and then that will increase the burst rate, so the likelihood of observing an exploding black hole. But of course, we cannot really increase FPVH because that enters in tension with the EGRB constraint that I showed in the previous slide. However, we can do the following. We can keep FPVH fixed and as low as 10 to the minus 10, but we can consider a situation where we have lighter black holes. That's the scenario on the right. And so if we reduce the mass of the black hole, we increase the number density, and so we increase the local burst rate. So that's one way to make it more probable for us to observe an exploding black hole. But of course, the problem here is that if we consider lighter black holes, where the lifetime of this black hole is also shorter. So if they form in the early universe, these light black holes will explode shortly after formation. They won't last the age of the universe, so they won't explode today. So we won't explode these light Schwarzschild black holes today. So, well, we can rephrase this question of how to enhance the local burst rate, and we can ask, how can we produce light black holes that will enhance the burst rate, but which are cosmologically long-lived? So how can we produce light black holes whose lifetime is the age of the universe? And so we have thought of a scenario where this can be realized. And the way it works is the following. So here in the plot here, I'm showing the evolution over time of the mass in blue and the temperature in orange of a black hole. Imagine you form a black hole in the early universe with mass 10 to the 13 grams. If that black hole is Schwarzschild, well, the lifetime is around 10 to the 4 years. So we want the black hole to explode at the at T universe, this thin gray line on the right. But this black hole is not something we're going to observe today. So how can we extend the lifetime of a black hole so that it survives the lifetime of the universe? And one option is going to quasi-extremality. What do I mean by quasi-extremality? Well, what I mean by that is that either the charge parameter, which is the ratio of the charge of the black hole over the mass of the black hole, or the spin parameter, which is the same but for the spin of the black hole, tends to 1. And so when one of these parameters tends to 1, then the temperature of the black hole tends to 0. So if the black hole temperature tends to 0, then Hawking radiation is essentially halted. So the black hole is not evaporating anymore. It just stays well stable, and it's just moving there in the universe without evaporating. It's hard to think of a scenario where a black hole can keep a spin parameter close to 1, because when the black hole starts spinning, the evaporation of non-zero spin particles is enhanced. So as soon as the black hole has a significant spin, it will rapidly emit particles with non-zero spin and go back to a social configuration. So that's difficult to realize a scenario thinking of rotating black holes. However, we still have an option with the charged black holes, the Reisner-Nordstrom black holes. And the way it works is the following. For charged black holes, it is also true that when a black hole has a significant charge, particles with the same charge, well, the emission of particles with the same charge will be enhanced. However, we can think of a scenario where we have particles beyond the standard model that are charged under some dark charge, which is not the usual well, standard model electromagnetic charge, but some dark charge. And it happens that the particle that carries this charge is very massive. By very massive, I mean, well, the condition you see in the slide. The mass of this black hole that carries the charge is way larger than the temperature of the black hole. So in this case, even if the black hole has a very significant charge, because the mass of the particle that carries this charge is so massive, the black hole cannot emit this charge. So it will just retain the charge and just lose mass via the emission of non-charged particles. So we can have a black hole that tends to extremality in this way. You might also worry about black holes accreting particles from the surrounding plasma and well, neutralizing the black hole and pushing it back to a social configuration. But we can think of scenarios that lead to a low accretion rate. And some of them are discussed in the references that you see on the slide. Or you can ask me later if you want more details. Okay. So if we stick with this scenario with charged black holes, as I said, we can think of a model where we have the standard model plus an extension of it, which is just a dark U1 extension. So you see there's a dark photon and a dark electron and a dark positron. And well, basically the mass of the dark electron and dark positron is extremely heavy, so that the black hole cannot emit them, and cannot get rid of the charge. Sorry. And well, now we can study what's the evolution for the mass and the charge of the black hole. Right? You see the equations here, and we can solve these equations numerically. Okay, so this is the situation we had with social black holes. Now, if we consider this toy model for this dark U1, and we have black holes that are initially formed with a very tiny charge in the early universe, we have the following. Well, this is the same plot, but in red, that's the evolution of the charge, actually the charge parameter, sorry, which is the ratio of the charge of the black hole with respect to the mass of the black hole. And the evolution of this charge parameter follows the axis on the y-axis on the right, where the numbers basically correspond to the numbers of 9 after the comma. So 0 is Schwarzschild, 5 is 0.99999, So very extremal, 10 is even more extremal, 15 is super extremal. Well, I mean, not super extremal, like beyond extremal, just very close to one, I mean. Um, and so what we see is that if a black hole forms in the early universe with a mass of 10 to the 13 grams, if it was Schwarzschild, it would explode after 10 to the 4 years. But now, because it has a dark charge, an initial small dark charge, uh, this black hole will just emit standard model species, so it will lose mass following the same evolution as the social black hole. But eventually, because this black hole cannot get rid of the charge, well, the ratio Q over M will tend to 1. And at this point, you can see that the mass just stays flat, almost flat. That's not really flat. And you can see that the temperature in orange just drops very significantly when the charge in red increases. So this is a way to extend the lifetime of the black hole via this quasi-extremality state. And by the way, this is an example of just one realization of this toy model. You can see above the plot, the mass for the dark electron is 10 to 10 GeVs, so very, very heavy. And the coupling is 10 to the minus 3 times the standard model coupling. Okay, but now I've been talking about exploding black holes. So we somehow want these black holes to explode today, right? And so from this plot, it doesn't seem obvious how these black holes can explode because they are quite extremal. So you said Hawking evaporation is very suppressed here. But the way it works is that it's following. As black hole loses mass and it keeps the charge, it becomes more and more quasi-extremal. Uh, and even in the quasi-extremal state, the black hole is still evaporating. It's just emitting the massless particles of standard model, mainly photons and neutrinos, and it's losing mass at a very small, very suppressed rate. And so that means that the electric field, dark electric field in this case, generated by the black hole is getting stronger. And at some point, this field at close enough to the black hole is so strong that it can produce pairs of dark electron and dark positron via the Schwinger effect. And because this field is so strong, the particles that have opposite charge just fall back into the black hole, and the particles that have the same charge they're just expelled to infinity. And so in this way, the black hole can quickly discharge, and also it loses mass, by the way, and kind of go back to a Schwarzschild configuration. And that's so the process is something well, you can see it in this sketch in the slide. You have a black hole with some charge minus Q, it produces pairs close enough to the black hole. And so in this case, the dark positron just falls back into the black hole, reducing the charge of the black hole, and the dark electron just goes to infinity. And so how does it look like in the evolution of the black hole? Well, this is the situation we had that I showed you in a couple of slides before. Now, if we take into account the Schwinger effect, what we see is a very sharp transition, a very quick discharge process. So you can see, for instance, in you can see the red line, which is the charge of the black hole. It very quickly drops to 0. Actually, the red line and the blue line are overlapped. So it very quickly discharges. It very quickly shifts from a quasi-extremal state to a Schwarzschild state. And when it goes back to a Schwarzschild state, well, this black hole is very light. It's 10 to 11 grams or so, which means that this black hole explodes well, very, very quick. Okay. And okay, so this is the evolution of a black hole for one example of the dark sector, so the mass of the dark electron and the dark coupling. And you can see how we can produce light black holes, which are cosmologically long-lived and have the whose lifetime is the age of the universe, right? You can tune the parameters and find the right mass for the black hole such that it explodes today. And now that's for one black hole. And I imagine we have a population of black holes that behave like that. Now, how do the constraints look like for this population of black holes? Well, now, as I said, the lifetime of the black hole is still the age of the universe, but now the mass at formation of these black holes is not 5 times 10 to the 14 anymore. That's just for Schwarzschild black holes. Actually, the mass formation depends on the initial value for the charge, for the black hole, and the parameters of the dark sector. And so we computed these indirect bounds for different scenarios, here labeled by A, B, and C. That you see they correspond to different masses and different couplings. And so that leads to different initial masses for black holes exploding today. And well, basically you see that the bounds that we get are essentially the same as the CMB bound in blue and the EGRB bound in black, but they're just squeezed and then shifted to lower masses. And they're just squeezed because the dependence of the evolution of black hole on the dark parameters, it's very sensitive, and actually on the initial mass of the black hole as well. So if you take a black hole that is slightly more massive than it should be, it means that this black hole stays quite extremal today. And if you take a black hole with mass less than what it should be, this black hole exploded already in the past. So only for a very narrow range, we'll have black holes that explode today. And well, you see that we managed to get an FPVH that is lower, which makes sense because these black holes, well, initially, remember that they behave like Schwarzschild. So they basically lose here 99% of their mass very early in the universe, very early in the universe. And then they only lose 1% of their mass in the late universe. And it's only this 1% that enters into the constraints like the EGRB, for instance. So it makes sense that we obtain roughly 2 orders of magnitude less in the FPVH. But also what's most importantly is that the population of black holes is now lighter. So if you recall the equation for the number density, which is here on the right, well, you see that for these scenarios, A, B, and C, we'll have an enhancement of the number density, and so we can expect an enhancement of the local burst rate. Now, we scan the parameter space for the dark sector. Now, this is a very busy plot, but let me explain it to you. On the x-axis, we have the mass of the dark electron. And then on the y-axis, we have some combination of the dark coupling and the mass of the dark electron. But if that's confusing for you, you can just look at the diagonal thin black lines, which correspond to the dark coupling. So that tells us our parameter space. And well, on the upper right corner, the region that is shaded in gray, that corresponds to values for the coupling constant, which are above 4 pi, which corresponds to, well, a situation where we lose perturbativity, which we're using to derive our equations. So we cannot trust our equations above these values of the coupling constant. And on the lower left corner, this is a condition that is required to apply the equations that I showed in one of the previous slides, which basically tells us that when the Schrödinger effect becomes effective, the particles with the same charge as the black hole, they're just expelled to infinity. They do not fall back to the black hole via gravitational interaction or anything. Basically, it's telling you that the electric interaction is stronger than the gravitational one. Okay. And well, the different colors in the plot follow the bar legend on the right, which is the maximum local burst rate that is allowed by the indirect constraints. So all these points here are consistent with the EGRB, CMB, and BBN bounds. And we compute what's the maximum local burst rate that is consistent with those bounds. So you can see now that we find regions of parameter space where the local burst rate can be as high as 10 to the 4 explosions per cubic parsec per year, which is a huge enhancement with respect to the values that we get for Schwarzschild black holes around 0.1 or so. And now we can compute what's the probability of detection at Hog on LASSO, assuming a period of observation of 10 years. and of course imposing some threshold on how many photons we want to observe to call an observation, right? Um, and so these are the purple and yellow lines that you observe. And well, very surprisingly, you can see that for a hawk, there's a significant region of space where the probability of detection is 30% and even larger, which is already quite optimistic. But for lasso, which has a well, better effective area and better um, properties than hawk, for most of these uh, region of parameter space, the probability of detection is around 90%, which is very, very surprising and very optimistic. So this plot here, the figure of merit of well, the whole presentation. And
Sorry, we have 5 minutes left.
okay, fine. Um, and well, it shows that a detection of primordial black holes in the next 10 years, assuming the assumptions that I discussed, is very probable. Um, okay, so I have 5 minutes left, so I will only, I don't want to rush over my slides, so I will only discuss now what's the connection of these exploding black holes with neutrinos at KM3net and IceCube. Well, those who followed the previous presentation are aware that earlier this year, there was an event reported by KM3net about a very high energy neutrino at around 200 TeVs or so, which is very surprising because it wasn't detected by IceCube. And IceCube has been observing the sky for longer than KM3net, but also all of the events detected by IceCube are around 1 PeV, which is basically 2 orders of magnitude below what was observed in KM3net. And well, people have discussed many scenarios in order to conciliate these the observations here. And the one that seems to be most favored is a transient point source. I think it was 1.6 sigma or something like that from the previous slide. And well, of course, I was interested in linking this observation with an exploding primordial black hole, right? Because as I said, a black hole, when it explodes, it reaches very high temperature. So it can emit very high energy particles, and it can easily produce neutrinos at such energies. And well, of course, many other people considered primordial black holes, and actually they were more ambitious. They tried to explain not only the KM3net event, but also they tried to explain those events detected by IceCube, which are not associated to a known astrophysical source, which you can see in the table here. And what they find is that if you consider primordial black holes, Schwarzschild primordial black holes in the standard model exploding today, well, the burst rate should be around 10 to the 3 in order to explain the events at IceCube, and 10 to the 6 if you want to explain the event at KM3net, which but induces that tension, right? Because if you assume that the KM3net neutrino comes from a black hole, so that leads to a burst rate of 10 to the 6, then you should expect way more events at IceCube. And if you assume that instead that the IceCube events come from a black hole, then that leads to a burst rate of 10 to the 3, which means that what was detected in KM3net is very unlikely that comes from a transient primordial black hole. And well, on top of that, if well, you remember one of the first slides in this presentation, for Schwarzschild black holes, the reasonable burst rates are around 0.1 or maybe 1, depending on the exact mass function that you use. As well, you can see in these two plots here, that's for a generalized critical collapse mass function. Doesn't really matter what these words mean. Just look at the numbers. The burst rates that are inferred with this mass function for Schwarzschild black holes are 1, 0.1, 1, something like that, which is very far from the burst rates that you need to explain IceCube and KM3net. So that adds an extra tension. And so we think that our scenario of these exploding black holes going through quasi-extremality can explain and resolve these two tensions. The first tension is clear already by looking at this plot. You can see that the maximum burst rate can go as high as 10 to the 4, and even more, it could go 10 to the 5, 10 to the 6, if you go lower in the parameter space. So it's not a problem for us to reach such high numbers. And for the second tension, we can solve it in the following way. remember, black holes that go via quasi-extremal state, well, they start like Schwarzschild, they go quasi-extremal, and then they go back to Schwarzschild. They discharge very fast, and then they explode. And so consider this scenario where well, we're just looking at the final bit of the PVH evaporation. So when it's quasi-extremal and then it goes back to Schwarzschild and it explodes. This discharge between going from quasi-extremal to Schwarzschild is very fast. It's very fast, and it can actually be considered to be instantaneous. It's really not, but for simplicity, we consider that it goes from quasi-extremal to Schwarzschild instantaneously. And when it becomes Schwarzschild, it has a mass ms1 that you can see here. Now, if we consider the neutrinos that are emitted by these primordial black holes, well, it kind of follows the time arrow, right? Because when it goes extremal, it's very cold, and at high energies, TB, PV, it's emitting zero neutrinos. When it becomes Schwarzschild, it starts becoming hotter, so it starts emitting more and more neutrinos, and you would see some shape like the one you see in the scheme. Well, don't take it too seriously though. Now, if you consider those neutrinos that can explain the ice cube events, are those that are above 1 PeV, and that leads to a burst rate of 10 to the 3, as I said. However, those neutrinos that can explain the KM3 net event are those that are above 35 PeV, and that leads to a burst rate of 10 to the 6. So here there's a clear attention. However, now consider this other scenario where a black hole becomes Schwarzschild at a mass ms2, which is way smaller than ms1. Now, because the mass is way smaller, when it starts emitting, it does so at a very high energy, higher than in scenario B. And so in this way, you can suppress the neutrinos that can explain the ice cube and keeping the same amount of neutrinos that can explain the K-3 net event.
We have 1 minute left.
Okay, thank you. Well, by suppressing ice cube neutrinos and keeping the same K-3 net neutrinos, we can enhance the burst rate consistent with the ice cube events and kind of resolve this tension. And well, for more details, you can just check the papers for the exact results. But just keep in mind that with this scenario of quasi-extremal black holes, we can enhance well, the local burst rate for ice cube and keep the K-net local burst rate pretty much the same. And so, well, in the end, if you look at the plot on the left, we can reach a situation where the ratio between the burst rate is 1. So it's the inferred burst rate for ice cube and the inferred burst rate for K-3 net is exactly the same, which leads to well, the tension being solved. And that happens for a very specific region of parameter space, which is very down the plot that I showed you. So following those black arrows beyond the x-axis. Okay, so I'll just skip the rest of slides because I don't have time, and I will jump directly to the conclusions. Well, I hope you agree with me that black holes are very interesting objects, even though we do not have any observational evidence. And however, we could observe a black hole in the coming years via the gamma ray and neutrino channel, since these black holes in the end they evaporate into very high energetic particles. And we have the technological capacity to make the observation, so we need to be ready. And so I presented a scenario, explicit scenario that leads to good chances of seeing an exploding black hole. And so I hope you agree that it's both possible and probable that we observe a black hole, exploding primordial black hole in the coming years, at least under the assumptions that I discussed. And also, interestingly enough, these black holes can be linked to the K-3 net event, which is very timely. So that adds an extra piece of interest for studying these sort of scenarios. And well, as I said, since black holes can operate into all particles beyond the standard model and also standard model, there's the potential to probe dark sectors, and we are currently working on that with a group at UMass. And we'll release a paper soon showing our results and our conclusions on this topic.